This evening we're going to be going over a conservation of energy problem. Specifically, we're going to be looking at a car and going around a track and going around a loop. So our tracks look something like this. It's going to be simply a ramp and then a circular loop, and the car is going to exit on the other side. So our overall height of our ramp is going to be denoted as h, and our loop is going to be of radius r. The car is going to start up here at the top. It's going to be held still, and then we're going to let it go. We're going to call this point, point 1. Whenever we let it go, it's going to roll down the track. It's going to pick up velocity as it gets down the ramp, and then at the bottom of the ramp, it's going to be going as fast as it's going to go throughout the entire system. So there's the car at the bottom of the ramp. We can assume no air resistance, no friction or anything like that, so it's an ideal scenario. All right, so at the bottom at point 2, it's going to be going the fastest point. So this is going to be labeled, like I said, point 2. And then the car is going to enter the loop. It's going to lose some of its velocity as it goes up and around, and it's going to pick the velocity back up as it exits the loop and comes back down. Okay, so there it is at the top of the loop. We're going to call that point 3. So our task is to figure out how high we need to make h so that the car makes it around the loop and does not fall off. So r is going to be a constant size. Okay? So how do we go about doing that? Well, we're going to use the conservation of energy. Conservation of energy states that the entire amount of energy inside of a closed system remains constant. So how do we apply that to this problem? Well, the two types of energy that we're dealing with are going to be kinetic energy and potential energy. Potential energy is the object's energy due to its position. It's defined as the mass times the gravity times the height. Kinetic energy is an object's energy due to motion. It is defined as 1/2 times an object's mass times its velocity squared. Okay? So let's look at the car at each one of the points. At point 1, it has a certain amount of potential energy. That's going to be equal to the mass times the gravity times its height. In this case, our red h is equal to our blue h, right? And it has some kinetic energy, which is equal to 1/2 times its mass times its velocity at point 1 squared. The velocity at point 1 squared, the velocity at point 1 is equal to 0, so therefore your kinetic energy at point 1 is equal to 0. At point 2, your potential energy, still the same definition, mass times gravity times height. However, your h at point 2 is equal to 0, so therefore your potential energy at point 2 is equal to 0. Okay. However, your kinetic energy at point 2 is not equal to 0. It's defined as 1/2 mass times velocity at point 2 squared. Well, basically the conservation of energy states that since the energy within the system has remained constant, you can't lose any energy. This means that our kinetic energy at point 2, so 1/2 mv squared, is going to be equal to our potential energy at point 1. Okay? So that potential energy is going to be transferred into kinetic energy. Point 3 gets a little more complicated. You have potential energy, still equal to mgh, However, your h at point 3 equals 2 times the radius. So your potential energy at point 3 equals 2 mg r. Your kinetic energy at point 3, 1/2 mass times velocity at point 3 squared. Keep in mind, we don't know what this is. We can solve algebraically for your velocity at point 2, although it's not important to solving this problem. We can solve for it if we need to by setting 1/2 mv squared at point 2 equal to our potential energy at point 1 mgh, and we can define the velocity in terms of h. That's going to be our maximum velocity in your system, not important for the solving of this particular problem. All right, so we can obviously see that velocity at 3 is going to be less than our velocity at 2, and our potential energy at 3 is going to be less than our potential energy at 1. So how do we actually figure out the relationship between these two? Well, to do that, we have to look at the forces acting on the car at point 3. We actually have two forces. Well, the first one's pretty obvious. The first one is the force of gravity. It always acts in the down direction, right? So gravity acts in the downward direction. That's going to be equal to the mass times the gravitational constant. We also have something called centripetal force acting on the car at this point. Centripetal force is the force that pulls the car towards the center of the circle. It always pulls it towards the center of the circle. Okay? So centripetal force always pulls you towards the center of the circle. Centripetal force is equal to mass times the velocity squared over the radius. Actually, let me put these in green. Typically, we're going to put functions or formulas in green that you're going to need to memorize. So, force of gravity equals mass times the gravitational constant. Centripetal force equals the mass times the velocity squared over the radius. Okay? So, in this case, we got to look at what happens whenever one overcomes the other. If gravity is greater than centripetal force, the car is going to fall. However, if centripetal force is greater than or equal to force of gravity, the car is going to stay on the track. Whenever centripetal force is equal to gravity, that's going to be our minimum velocity that we can actually maintain contact with the track. The minimum velocity that we're going to maintain contact with the track happens at point 3. So therefore, we can set centripetal force equal to gravity to find the velocity at point 3. And that will give us part of the overall energy of the equation. And then we can set that equal to our potential energy at point 1 to solve it. So let's go ahead and do that. Okay, so we know that our centripetal force is equal to our gravitational force, which means that our mass times our velocity at point 3 squared over the radius is equal to our mass times our gravity. A lot of masses are going to cancel out, giving us our velocity at point 3 squared over the radius is equal to the gravitational constant. Therefore, our velocity at point 3 squared is equal to a gravitational constant times r. So your velocity at point 3 is going to be equal to the square root of gr. So therefore, we can actually plug it into that equation to get our kinetic energy at point 3. So our kinetic energy at 3 is going to be equal to 1/2 mass mass times velocity at point 3 squared equal to 1/2 the mass. We'll substitute in our square root of gr for velocity of point 3. Square root of gr squared, which is going to be equal to 1/2 mgr. Remember, our potential energy at point 3 is going to be equal to 2 times the mass times the gravity times the radius. And your total energy within the system, so kinetic energy plus potential energy, is going to be equal to your potential energy at point 1 plus your kinetic energy at point 1. That was 0. Plus your potential energy, point 2, plus your kinetic energy at point 2. You made a slight mistake there. This should actually be an equal sign. Okay, so total energy is still constant within the system. Remember, our potential energy at point 2 is also equal to 0. So therefore, we can actually add these two together and do some algebraic substitution and solve this thing. Okay? So let's expand this out. So kinetic energy at point 3. Let's pull that back down a little bit. Kinetic energy at point 3 is equal to 1/2 mgr plus your potential energy at point 3, 2 mgr. It's going to be equal to either our potential energy at point 1 or our kinetic energy at point 2. We're trying to find it in terms of h, so we're going to use the potential energy at point 1. So our potential energy at point 1 is simply equal to the mass times the gravity times the height. Okay? Notice that every term has a mass in it, so our masses will all cancel out. And what you have left over is 1/2 gr plus 2 gr equals gh. Additionally, our g's will cancel. So 1/2 r plus 2r equals h. So therefore, we can simply solve this and say that h is equal to 5/2 r. Or another way of saying this is r is equal to 2/5 h. And that's how tall our h needs to be, our ramp needs to be, to make sure that the car does not fall off the track. Another way of saying this is if we have a ramp of a constant height, we can't make the radius more than 40% or 2/5 of the height of our ramp.